Hi everybody. Congratulations, you've finished chapter 1 of physics, that is the math review. And now we're going to getting into what I think is the real fun of physics, just the applying this to everyday events. By the way, just as a little disclaimer, hopefully you aren't hearing this in the background. My wife is doing P90X, and hopefully the the video is not too loud. But anyway, if it is, let me know. Otherwise, we'll just keep going like this. So this is chapter 2, one-dimensional kinematics. Now the idea of kinematics is the same idea that is in the root word of like kinetics, or if you're going to college, this idea kinesiology. That is motion, the study of motion. So that's what this is, and so understanding how we describe motion and how we measure it. So first of all, we need to identify how we describe quantities. And when you have a quantity, there's really two parts to it. There's the magnitude. In this case, we've got 23. All right. And then we have the unit as well. But so this right here, 6 feet. We've got 6 and 23. All right. Well, that's great. But if you ask somebody, hey, how cold is it outside? Well, it's 23. That's either good or bad. If you're talking about Celsius, that's pretty good because that's about room temperature. If you're talking about Fahrenheit, that's pretty horrible because it's pretty darn cold. Same thing, 6 feet tall. 6 feet is about the right height for a man or a fairly tall man. 6, I don't know, inches, meters. That's a different story altogether. So the magnitude is really just the number that is out in front of the unit. Okay. All right, so we got 23 degrees, we've got 6 feet, so on and so forth. But what's really important here is to define whether something is a vector or it's a scalar. These are two different ways of measuring a magnitude of something that can be quite different. Let's start with a scalar right here. So a scalar quantity only has a magnitude. And we have listed here, mass and temperature and distance. But let's look at this distance here for a second. I'm thinking of a movie, which maybe you've seen before, maybe you haven't, I don't know. Ferris Bueller's Day Off. All right, and if you've seen it, it's awesome. If you haven't, it's pretty funny, and you should see it. But the one guy takes his dad's Ferrari out without asking, and it winds up getting all kinds of mileage put on it. All right, so this is our Ferrari right here, and it's tons, like thousands of mileage or hundreds of miles worth of mileage put on it, which is pretty bad. Okay, so they think, hey, let's just put it up on jacks in the garage before Dad finds out, and let's put it in reverse, and just have it in reverse and have the wheels spinning. All right, so maybe that'll reverse the odometer. I mean, the odometer is the however many miles you have. That's the odometer on the engine. All right, what that counts is how much wear and tear the engine has taken. Well, the engine doesn't care if the wheels are spinning forward and backwards. The odometer is still counting upwards. So whether it's in reverse or forwards, it's still counting up. So you can call that a scalar quantity. It just has a magnitude, whether it's 10,000 miles forward or 10,000 miles backwards. It doesn't matter. It's still 10,000 miles worth of wear and tear on the engine. And so you can think of that as a scalar. On the other hand, a vector quantity is something that can have a positive or minus. That is, the direction actually matters. We've got a few values right here that will probably make sense to you later on, position and force. But I think of it like this. If we have a game of Monopoly right here, and so you got all your, around the edge, you've got all your little things that your little blocks that you move through and stuff, and in the middle that's where you put your cards and everything, and that's great. But a vector quantity can have a positive or negative value. So you might have your little piece right here. Here's the, I don't know, I'm in car mode, so I'm going to draw the little car. All right. You might roll something that says move X number of spaces forward, five spaces forward. That's great. But then you may pull a chance card that says, uh-oh, you go to jail or something like that, or if something bad happens, move. I should have drawn that in green. Oh well. I'm going to draw this one in green. Move X number of spaces backwards. All right? That's bad. The more spaces you move, the more the spaces that you move doesn't matter. What matters is that you're moving it in the positive direction. That's what really matters. So you get to the end of the board and, get another set of cards or something like that. So that's the idea between a scalar, which is all, you might say, the absolute value. Think of the odometer of a car. And a vector, which can have a positive quantity or a negative quantity, depending on what the direction, or you might say, or depending on what the coordinate system is right here. An average Jeopardy game has a coordinate system that's positive, and this direction is negative. All right, so there's forward and backwards on. Have I been saying Jeopardy? I'm sorry, I meant Monopoly. Hopefully I said Monopoly. Oh gosh. Yeah, I meant Monopoly. Yeah, so I meant Monopoly. A Monopoly game, has a forward direction and a backwards direction. So you can think of that as a vector. All right? Whew, Jeopardy. Oh, goodness. All right, next. So let's introduce the idea of position. Position is simply a location. And it's a location with respect to a coordinate system. In this example right here, look, the coordinate system starts right here. We call this location 0. Position, or x equals 0. And so this guy who's standing right here, his initial position, never mind how he got there, but his initial position now is, well, probably some direction positive of 0, right? Let's just pretend that's, I don't know, 3 meters. We indicate this by saying xi, that is x initial, all right? And then, of course, as you probably guessed, as he moves over a period of time, this is his final position. Let's say perhaps that's, I don't know, 7 meters. So x final equals 7 meters, x initial equals 3 meters right here. Okay, so wherever we have an arrowhead, that indicates a positive direction. So as you move more this way, he's going to get more and more positive. Or as I sometimes like to say, positiver and positiver. Okay, now if you were to move this way, he'd be going negative, and so his position would decrease, even to the point where if he were over here, he would have a negative position. He would have a negative, it's a negative 3 meters. He would have a negative location on this coordinate system. So all this is with respect to some coordinate system that either you or somebody else establishes. Okay? So that is position. By the way, we call it X because as we're starting out right now, we're talking about, an x-axis, or might say a horizontal axis. So initially, we're talking about displacement or moving along a horizontal axis, so that's why we call it X. We'll give position axes different names if we're talking about different axes, but now we're just going to call it X. So in the same way that we have a scalar and a vector quantity, we have what we call distance and displacement. Distance is the total length of the path taken. Okay, you can think of that again as the car up on jacks. Well, this is going to be a really bad car, I can just tell you right now. That's facing forward, but the car is in reverse. All right. Well, like I said before, the engine doesn't care. Oh, by the way, this is That's the front window right there. Like I said, it's going to be a bad Ferrari. That's front. All right, and so this arrow right here indicates reverse right here. The engine doesn't care what direction the wheels are spinning. And so it's just going to rack up more and more and more positive miles because it's a greater distance that the engine is turning. On the other hand, displacement is our term for, you might say, a positive or negative change in an object's position. But you need some sort of coordinate system, some sort of axis. That's positive, that's negative. You need some sort of axis to determine that. And so displacement is how much has something changed on a, you might say, a positive negative axis or positive negative scale. Very much like I said before, I think it's a Jeopardy, but I meant Monopoly board. Okay, if you move plus 3 spaces and minus 2 spaces, then you've gone a distance of 5 spaces. That's great, but Monopoly cares about displacement. So plus 3 minus 2, that's 1. That's not too great. So displacement is going to be positive or negative. Distance is going to be, you might say, the absolute value, or always positive. Our system, we're going to deal with the System International unit, or system, or in French, that means, you probably guessed, international system, also known as a metric system. So meters is going to be one of our main distances of measurement for distance and displacement. And as I think I showed you before, this equation right here describes how much something changes position. This value, this, you might say, this symbol right here, that Greek D or delta means change in something. So if our final position equals 7 meters and our initial position equals 3 meters, we moved from 3 to 7. So you can say, okay, our change in position equals 4 meters. That's the whole concept behind that. So you always take your final minus the initial, and that'll tell you what the change in direct or in distance or displacement is. All right, so let's do a little example right here. And I think the next slide or next screen is blank, but I'm just going to do it right on the screen because it's easier and we have this nice diagram in front of us. So you're invited to a party at your friend's house. You need to pick up some soda from the grocery store. So this is you right here. You need to go to the grocery store, get some soda, and then you need to get to your friend's house, which is right there. All right, so you need to go from here to here. You know what? I'm going to stop doing that. I'm going to go forward with green and backwards with red. So from here to here, and then from here to there. All right? So the reason I did that, I'm going to call green the positive direction and red the negative direction right here. And that'll come in handy in just a second. I'll put those in parentheses right here. So the first question is, what distance must you drive or walk or whatever for the trip? What distance? Now, distance, remember, is a scalar quantity. Doesn't care about direction. It just cares about how much, you might say, mileage that you log. All right? Well, you go 4.3. Let me write distance right here. Distance equals 4.3 in that direction. All right? 4.3 miles. And already we're breaking our rule of using the metric system only. And then minus 4.3 miles, but doesn't matter, you're still logging 4.3 miles. So 4.3 and 4.3. So you're going to log another 4.3 miles plus another 2.1 miles, right? 2.1. So 4.3, 21 point, that doesn't work. 2.1. 4.3 plus 4.3 is, what's that, 8.6 plus 2.1, it's 10.7. 10.7 miles you have to walk to go from your house to the grocery store to your friend's house. All right? That's kind of a pain. But let's see what your displacement is, and maybe if this sounds any better. All right? Displacement is equal to, all right, so you've got plus 4.3 miles in the positive direction, plus, what do we have right here? Well, we've got 4.3 and then 2.1 miles in the negative direction. Okay, so I'm going to put these in parentheses right here. Negative 4.3. Remember, this is because we have a negative because it's a displacement. Negative 4.3. Close the parentheses right here. Plus negative 2.1 miles in the minus direction. So again, if we call this location right here 0, and that's positive, and that's negative, well, look, you're going to wind up eventually in a negative direction because you're going negative from your house to your friend's house. So the question is, exactly what direction negative, or how negative is that? Well, 4.3 plus negative 4.3, well, they just cancel out, right? And so your final answer is going to be negative 2.1 equals negative 2.1 miles. I'm going to box that right there. To go from your house to your friend's house, your displacement is negative 2.1 miles from start, x initial, to x final, even though you went way out of your way to the grocery store and then all the way back to your friend's house. So from here to here, delta x equals negative 2.1 miles. All right, so the distance is clearly very different from your displacement, but it depends on where you start and where you finish. And that's our blank page I said we'd skip. All right, so now we're going to do like another little example right here, and that'll be it for this section here. So we have an x-axis, and right off the bat, I'm going to draw an x-axis. All right, so that direction is going to be positive, and the opposite direction will be negative right here. And I'm just going to, right here, call that 0. Okay, so we've established a coordinate system. And so if we've got a coordinate system, we must have displacement because you can be positive or negative on it. And so, of course, the question is asking us about displacement. So first of all, it is located at x equals negative 1 meter. All right, well, let me just draw some tick marks in here. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. All right. So initially, so x initial equals negative 1.0 meters. All right. So negative 1.0 meters. That's negative 1. That's positive 1, right here. So that's going to be our x initial. Okay, and so then it experiences a displacement. Remember, displacement is, hold on a minute. Kawa, you stay here. Sorry, my dog's kind of running off. A displacement is a change in position, right? So our delta x equals 5.5 meters. Now notice there's no negative in front of it, so it indicates that it must be a positive 5.5 meters. And so it goes from this location here, negative 1, and it is displaced 5.5 meters. So it goes 1, 2, 3, 4, 5 and a half. Delta x equals 5.5 meters. 5.5 meters. Right here. All right? Delta x equals 5.5 meters. So, what is our final position? What it's asking us is, what is x final? Well, we can see on our coordinate system right here, that's pretty easy to figure out. We have It goes 1, 2, 3, 4, 5.5. So that means the final position, x final, is going to be 1, 2, 3, 4.5 meters on the positive direction. All right, equals 4.5 meters. But you probably could have figured that out because remember our equation for displacement is delta x, that is a change in displacement, equals x final minus x initial. Okay. So if we want to solve for our final position, this right here, how do we solve for that? Well, we just get the xi away from it. So that is, we say x final is going to be delta x. Let's see. I can write this a couple different ways. We'll just add xi on this side. So we have to add it on the other side. So plus x initial right here. Well, our displacement is 5.5 meters. All right. Plus our initial position was, recall, that was -1 meter, or 1.0 meters. All right. So our x final is going to be 5.5 plus -1. Of course, that's 4.5 meters. That's our final position right there. So you don't have to draw an axis every single time and then count notches over. You can just take x final minus x initial equals our change in displacement. And so that's how we can find our change in displacement. That's it for now. I'll see you guys in the next video.